So it's true that electromagnetic force is stronger than gravitation, but they're not the same. So remember how gravitation is an always attractive force. Always attractive. Two bodies with mass will always be attracted to each other. Electromagnetic force is stronger than the force of gravitation, but it is sometimes attractive and sometimes repulsive. Like charges are repulsive towards each other and opposite charges attract. So gravitation and electromagnetic forces, these are not the same. They're not the same, okay? They're not the same. One is a lot stronger than the other, but first of all, both we're familiar with, and one of them is very universally present, which is gravitation. I mean, electromagnetism is present too, but what kind of, for example, we talked about large scale structure, right? What is sort of really important in cosmology is what's happening in the universe at a large scale. And at that scale, gravitation is a player, is a very important player. So we would like to understand it better. We really would. And so it's a bummer when it's not explained by quantum mechanics and particle physics, okay? Einstein's general theory of relativity is a classical theory in the sense that Maxwell's equations of electromagnetism are also classical. They involve entities that are smooth rather than discrete and describe behavior that is deterministic rather than probabilistic. So once again, classical will be smooth, quantum will be discrete. Classical will be deterministic, quantum will be probabilistic. Those are the differences. But also, the gaps are there as well. Classical cannot explain certain quantum things, and quantum cannot explain gravitation. That's the issue. So on the other hand, quantum physics describes a fundamental lumpiness. Everything consists of discrete packets or quanta. Likewise, the equations of general relativity allow one to calculate the exact state of the universe at a given time in the future if sufficient information is given at some time in the past. They are therefore deterministic, so deterministic. The quantum world, on the other hand, is subject to the uncertainty embodied in Heisenberg's uncertainty principle. Of course, classical electromagnetic theory is perfectly adequate for many purposes. But the theory does break down in certain situations, such as when radiation fields are very strong. For this reason, physicists sought and eventually found the quantum theory of electromagnetism or quantum electrodynamics. Remember, we talked about QED. It was basically quantifying or unifying electromagnetism with quantum. This theory was also made consistent with the special theory of relativity, but does not include general relativistic effects. While Einstein's equations also seem quite accurate for most purposes, it is similarly natural to attempt the construction of a quantum theory of gravity.